In geometry, we study how to get the area of, the standard figures, right? We know how to get the area of a rectangle. We know how to get the area of a triangle. We can even figure out how to get the area of like an octagon by slicing it into a bunch of triangles, like a regular octagon, not an arbitrary octagon, which is doable but much more difficult. Anyway, we can slice that into small triangles, get the area of each triangle, and then sum it up. But we don't study in elementary geometry how to get the area of arbitrary regions. So if I have this curve, and let's say that the bottom is here and the top is there, how would I possibly understand what the area of this region is? Well, in calculus, what we do is we can estimate it. And then we can learn that if we do it just right, our estimations become actualities. But let's start with the estimate. Let's go all the way back to the simplest of geometric shapes, the rectangle. You might say square is simpler. Square is a rectangle. But a rectangle says I've got a base and I've got a height. Simple enough. So what if I naively said, I'm going to figure out the area of this by, rectangles. I'm going to say, okay, I'm going to try to panel this thing with rectangles. So I'm going to split this thing up into, let's just say I split it up into 2 regions. And I say, all right, I've got 2 rectangles here. What do you think? You think that estimates it? It's not great. It's all right. It's not great. What if I say, okay, well, I'm going to take another crack at this. What if I do this piece? So I come up here, and then I come up here, and let's say, again, I cut it in half. And what I'm going to do is I'm going to take the function value at whatever x value that is. I'm going to take the function value and I'm going to slide it across. So I've got these 4 rectangles. That's okay, right? It's better. But I'm underestimating it here. I'm underestimating it. I'm overestimating it. I'm overestimating it. You may say, well, that all comes out in the wash. Well, it might. What if I do it again? What if I say, all right, I'm going to cut those in half? And you don't have to cut these in half. You don't. So, okay. All right. That's getting better though, right? I mean, by this point, your errors are and the vertical lines are underestimations and the horizontal lines are overestimations. And that's not bad. But what if I keep doing it? If I keep slicing that, what if I just keep slicing that piece by piece by piece by piece by piece by piece? Is that gonna work? Turns out it might. So what we can do is we can say that the area under the curve is representable as a sum of rectangles. So in each of these rectangles, they've got some sort of width, right? We don't know what. In this case, I always cut it in half. So, these are all evenly spaced. So if there's 1, 2, 3, 4, 5, 6, 7, 8, each of these 8 has the same width, and we'll call that width delta x. But they don't have to have the same width. You could have some have much smaller, much more narrow widths than the others. and then as you get them more finely, some of them get finer more quickly than the others do. But a lot of times, for simplicity's sake, for a lot of the functions we deal with, it makes sense to use a uniform width. What we can say is that that area under the curve is approximately some function value at that point times the width at that point. So we could say, all right, so in this case what I chose is I chose what's called a left-hand sum, where I took the left point, or I took the value from the left and went over, from the left and went over, from the left and went over. There is what's called a right-hand sum, where I start from the right and go over, from the right and go over, from the right and go over, from the right and go over. Now notice over here I'd be underestimating on these lines, but once I got over here I would be overestimating. And what you find is sometimes the right-hand sum makes more sense and sometimes the left-hand sum makes more sense. It doesn't really matter. But we know the area is approximately that height times the length of the base, right? It's the length of this base times the height. The length of the base times the height. And what this is chosen to be is based upon whatever sum you're trying to get to. And again, we say, left-hand sum you usually pick the values from A going all the way over. If it's a right-hand sum, what you're doing is you're picking the values from this point all the way to B. You're not, notice in the left-hand sum, you're not actually including B here. Notice I started here and I went over. I don't actually use this function value. So there's a left-hand sum and a right-hand sum. Now, those are gammas, and we're not going to be using that notation further from here, but just know that these are ways to sometimes represent this. You may see that in other notations and other resources you use online. You'll see these left and right-hand sums, but generally speaking, we will be using S as our notation for the sum, and specifically, we will use S sub n to represent the sum of n equally spaced partitions. Not really partition. Well, you could say partition here, but notice that since that's a constant, you can actually pull delta x out. You can say, well, that's delta x. So what you're doing is you can figure out that sum from I equals 1 to n, and then you can figure out what delta x is. And since this is some sort of n-based on the number of partitions, what if we took the limit as n approached infinity? What if instead of 100,000 points we took 1,000,000, 1,000,000,000, trillion, all the way to infinity? That width would squeeze super small. You might say, well, that's going to vanish. I mean, if it squeezes super small, that strip's going to vanish. That's true. But what you're doing is you're trying to determine, even though the width is vanishing, the total number of them is growing. So is the amount growing overall faster than the width is diminishing? And the answer will be yes, because clearly this has some sort of positive area. So it's not going to vanish to zero. But this is the idea. You have a left-hand sum, you have a right-hand sum that you can do, and you can equally space them. But what you find is that as n approaches infinity, it doesn't really matter if the strips are here or here, because all the pieces in the middle are really where the information is. And as those strips go to infinity, or the width that goes to infinity, those endpoints just kind of push out, right? They get so small, we don't really care if it's left or right hand. We care about all that mess in the middle, and it kind of just fills up the sums, and you find the sums are going to converge if they do. Sometimes the left and right hand will not converge. In that particular case, we would say that function is not integrable, but that's kind of beyond the scope of what we're trying to get to right now. But anyway, this is the basic form, and we're going to do some practice with this and talk a little bit about upper sums and lower sums.